So yeah, we are on. Welcome everybody, especially those watching on YouTube. Another Friday on Hilbert Spaces. Today you will start to learn about some of the important notions, namely about the operators. These are very, very important. So just as a motivation, Max is a mathematician, obviously, so he will walk you through this in a mathematical fashion. So it will be very abstract to start with, but this is something that you need to. That's why we are called quantum formalism, right? Is to be able to take this. But at the end of it, you will learn, very important notions, and this is really very important, to understand, the underpinning operators on Hilbert spaces. Not at least, you will learn with Carlos that, for example, some physical observables, things that, physicists measure, like say, for example, the energy, the Hamiltonian, are modeled by operators. In this case, special type of operators. It has a special name mathematically that you will learn later. For those coming from quantum computing, the quantum gates are the building blocks of the quantum circuits. Each gate corresponds to a unitary operator acting on the qubits. So if you want to do, design quantum algorithms, these are very important notions that you need to understand. In particular, the ability to be able to understand different type of gates, that will show up in your algorithm that you need. So this means that you need to understand about the operators. Okay, so that's the motivation. So without further ado, I will hand over to Max, and I will disappear. Max.
Hi guys. Yeah, thanks for the introduction. For those of you who haven't seen me before, I'm Max Arnott. I've just come through the Homotopic Minds course, and I've been working with Zaiku ever since. I also just finished my PhD, which was in operator theory. So this is very much within my wheelhouse. So the things we're going to talk about today, we're going to start off just by defining the operators on a Hilbert space and, what the space of these operators looks like, because the set of operators on a Hilbert space forms a vector space of its own, which has certain properties, and you can give it a norm. This norm is called the operator norm, which brings us on to our next topic. After then, we're going to go on to adjoint operators, and then we're going to finish off with a very brief look at the spectrum of an operator. If people were interested in the future, if there's an appetite for it, we could go into more depth on the spectrum of an operator in a future talk, because it's a very interesting topic and there's a lot to it, but it would require a whole separate thing of its own. So for the time being, we're just going to sort of go over what the basics of spectrums are. Okay, so if U, V, and W are Banach spaces over a field, real or complex, an operator is just a linear function from one to the next, V to W. Now, the reason that we are talking about Banach spaces here and not just Hilbert spaces is because a Hilbert space is a special case of a Banach space, which is something that was discussed in the previous lecture. So I tried to introduce more abstraction, if possible, whenever it's not going to complicate things further. And so yeah, if you're only interested in Hilbert spaces, you can think of Banach spaces as just a more generalized version of that. We denote the set of all operators from V to W by L VW, with L standing for linear in this case. And the subset of this set L here is this of the space of continuous operators is denoted by B V of W. Now, why would B stand for continuous? That's because the continuous operators are the same as the bounded operators, which is something we'll revisit in a few slides' time when we define all those things properly. Okay, so an exercise for you to try after the talk is to just show that these are vector spaces. A lot of the things in this talk, if it's an easy exercise, don't worry if you can't get it on the first try. I did just kind of make up these difficulties of these exercises off the top of my head. But yeah, this one, if you're familiar with how linear functions work, then it shouldn't be too much of a problem with you for you. Also, if you think it's going to be too easy or if you think it's obvious, still try the exercises because it's good practice. And you know, the worst thing that can happen is you wasted like 2 minutes. So definitely give them a go. I'd recommend it. Okay, so just a shorthand notation that everyone uses in operator theory. If you have the space of operators from a space to itself, you just denote it with one v here. So L of v is LV, and similarly B of v is equal to BV. And these have algebraic structure because of the fact that you can then compose the elements of this set here, BV. But that's beyond the scope of this. We're not going to talk about the algebraic structure of these so much today. And we write composition of operators by concatenation, which just means we're sticking them together, right? So if we have an operator S from V to W, an operator from T from U to V, then ST goes from U to W, right? Because T goes from U to V, and then S goes from V to W. So you've gone from U to V to W. And that just has action exactly as you expect. So applying S to TW is the same as applying ST to W. Okay, so moving on, we're going to define a function on the space of operators from V to W, where V and W are normed. And this function is defined as follows. So I'm going to call it the operator norm. That is its name, but we haven't shown that it's a norm yet. We will do eventually, but for now, it's not obvious that it's a norm. And in fact, it's not a norm on this space, but it's a norm on B of VW. So you have to be careful. So yeah, what does this function do? The operator norm of T is defined to be the supremum of the set of TV such that V has norm less than 1. V is an element of the domain of V. So norms are often thought about as sort of a way of measuring different elements of your vector space, right? And so how can we envision this as a measurement of T? Well, it sort of measures the largeness of T by saying, oh, if I've got lots of things that are in the unit sphere of V, what's the biggest T can make them? Like how big can T stretch these elements? So in that sense, it kind of measures the largeness of T. And it can be infinite for some linear operators, but never continuous ones, which is the key to what's coming up next and why these bounded ones are continuous. So yeah, this is what we're going to show next. We're going to show that the set of continuous operators from V to W is exactly the set of bounded operators from V to W, where we say that T is bounded if its operator norm is finite. And yeah, so to sort of see where this word bounded comes from, it's saying that if I have a collection of things and they all have norm less than or equal to 1, and I apply T to all of them, there's a bound on how big I'm going to get these. I'm never going to be able to make the size of this sequence of images of norm 1 vectors go bigger and bigger and bigger. So that's why it makes sense to call these things bounded. Another thing for you to try after the talk today is the following. So for norm spaces V and W, if V is non-zero, because otherwise it all becomes a bit trivial, let T be a linear function from V to W. And we're going to ask you to prove that the following equation holds. And this is just a bunch of different ways you can write the operator norm that are all helpful in different scenarios. So this is the one we've been introduced to already. For these next two, you're basically just playing around with the properties of the supremum. So if you understand and remember the supremums from your undergrad analysis courses, this shouldn't be a problem trying to get these equivalences. This one here, the fourth one, is kind of why you have to specify that V is non-zero, because otherwise, you're taking a supremum over the empty set if V was 0. So it's just a little technicality. And the last one, that one might be a little more challenging. But again, if you're comfortable with your supremums and your infimums, this one's not too bad either. Another thing that is a good exercise to show is that the norm of TV is less than or equal to the norm of T times the norm of V for every vector in the vector space of the domain of T. And this is a sort of like sub-multiplicative nature. Okay, so as promised, we're going to talk about how bounded operators and continuous operators are the same thing. So as a bit of a reminder, this is the definition of what it means for a operator to be continuous, or just any function to be continuous. So it's continuous at a point V0 in its domain if for all epsilon bigger than 0, there exists some delta bigger than 0, such that if the difference between V and V0 is less than delta, the difference between TV and TV0 is less than epsilon in norm. So it's basically saying that if T has a very small change in the codomain, it must have been caused by a very small change in the domain. And yeah, this is just repeating the definition of the operator norm so that it's on screen and like fresh in your minds. And here's the theorem. Let T be a linear function between normed vector spaces V and W. The following are equivalent. So T being continuous on V, T being continuous at 0, and the operator norm being finite, i.e. T is bounded. Now, the middle step here is a bit of a stepping stone just to kind of connect the two, but it's also, I find it quite interesting in its own right, because the equivalence of A and B here means that if you've got a linear function and you want to show that it's continuous on its entire domain, the only thing you have to check is one singular point. You just have to check that it's continuous there. So it's actually quite a handy little way of proving that something's continuous sometimes, if it's linear. Okay, so let's prove this. First thing we're going to do is A implies B. So it's trivial, right? If T is continuous on V, that means that T is continuous at every point in V, and V, contains 0. Just as an aside, this 0V notation just means that it's the specific 0 of the vector space V, not necessarily the scalar 0. If V was R2, then this would be, the origin of the plane. So yeah, I assume everyone's worked with vector spaces before and kind of knows that they all have a 0 of their own. But anyway, A implies B is obviously trivial. So next, we're going to do B implies C. So what do we have for our assumption? We assume that T is continuous at 0V. And what does that mean? Well, we'll just plug 0 into the definition of continuity. And that tells us that for all epsilon greater than 0, there is some delta greater than 0 such that if x minus 0 is less than delta, tx minus t0 is less than epsilon in norm. Now, for every linear function, when you plug in 0, you get 0. And what that means is that you're plugging in 0 into this equation here, or this inequality here, sorry, and what you end up with is this line just means that whenever x is smaller than delta, tx is smaller than epsilon, and that's true for every point in the domain. So we're trying to prove that the operator norm is less than infinity for t. So we're going to show that if we take an arbitrary element of V, which has norm less than 1, it can't be made arbitrarily large by t. We can find some upper bound on how big t can make this vector V. Right, so what we're going to do is let x equal delta V. And the reason for that is I've spotted here on this line if x is less than delta in norm, then we have a bound on the size of tx. And when we set x to have this definition, well, x is equal to delta v. We use the property of the norm that the absolute value of scalars can come out the front. And because delta is a real number and the norm of v is less than 1 by our assumption, we get that the norm of x is less than delta. And what does this tell us? Well, it tells us from this line that the norm of tx is less than epsilon. Finally, we just plug x equal delta v back in, or in other words, v is equal to 1 over delta x, which we can do because delta is non-zero. We can bring this out the front because it's a positive real number, and what we end up with is this inequality here. So the norm of tv is less than epsilon over delta. So whenever the norm of v is less than 1, the norm of tv has to be less than epsilon over delta, which is what we were trying to show in the first place. Now, the operator norm of t is the supremum of how big we can make these vectors v which have norm less than 1 when we apply t. So we've shown by definition of the operator norm that operator norm of t is less than or equal to epsilon over delta, which is of course less than infinity. So we proved that t is bounded. There's one thing left to show, and that's C implies A. So first off, suppose that t is bounded. Well, if t is bounded, then the operator norm of t is less than infinity, which must mean that it's less than some real number as well. So we're going to take a constant c, which is some positive real, such that the norm of t is less than c. Also, let epsilon be greater than 0, because we're trying to prove that something is continuous. Okay, so by the definition of the operator norm and the fact that it's bounded above by t, if v is an element of the domain of t with norm less than 1, we know that the norm of tv has to be less than c. That's just true by the definition of this. Now we're going to try and prove that t is continuous on v, which means that we have to prove that it's continuous at every single point in v. So we're going to let v naught be an arbitrary element of v, and what we need to find is a constant delta bigger than 0, such that whenever v minus v naught is less than delta in norm, the norm of tv minus tv naught is less than epsilon. For every v in v, I should say. And we claim that it works when we pick the constant delta equal epsilon over c. So with epsilon fixed, we have to find some delta. This is the delta we're going to say is one that works. So let's show that this works. So whenever v minus v naught is less than delta, we have to show that the norm of tv minus tv naught is less than epsilon. Well, if the norm of v minus v naught is less than our choice of delta, epsilon over c, then we can divide both sides of this inequality by epsilon over c and obtain this. The norm of c over epsilon v minus v naught is less than 1. Now what we can do is plug in the fact that we have upper bound of c on the operator norm. Now this fact means that t of this is going to be less than c. So t of c over epsilon v minus v naught, well, we can use the linearity of c to say that this, of t, sorry, to say that c over epsilon tv minus tv naught has norm less than c. And yeah, this shows that tv minus tv naught is less than epsilon as required, because you take this inequality here, you divide it by c, and you multiply it by epsilon on both sides. And that's how you get from this step to this step. So I hope that makes sense to everyone. I hope you're, it may have been a while since you've seen epsilon delta proofs. One thing that's always a bit difficult with these is, so when you're trying to prove that something's continuous, you say, oh, let epsilon be bigger than 0. What we want to do is find a delta that works. And it's very different to prove that a delta that someone has shown you works compared to finding a constant from scratch that works. So if you're asked to prove something is continuous, what I do is just plug in some arbitrary constant delta, sort of like go through all the steps, get to the end, and then it should be kind of apparent what choice of delta to take. So in this example, we could say, if delta is arbitrary, suppose that the norm of v minus v naught is less than delta, then the norm of 1 over delta v minus v naught is less than 1. And then we can use this step on it, and we'd get t of 1 over delta v minus v naught is less than c. And it's kind of at this point you'd realize that epsilon over c would be a good choice for delta. So yeah, don't worry if these take a while to get. They're sort of a bit lofty and abstract, and it's probably quite different from a lot of stuff that you learn in computer science and physics. This is like the purest of the pure maths, but it's a nice theorem, and it's really helpful. And yeah, definitely the equivalence of boundedness and continuity is something that you need to know and you need to take with you. Okay.
It's Carlos. I don't know if you can see the chat.
Oh, no.
It has some questions, and I can read the questions. I mean, I think the first one from Mohammad Riza, you just proved that what's the mean by infinite norm. And George, he writes something also. If it is greater than any real constant, but I don't know exactly, George.
So do you mean in this step, like why this being finite means that it has to be less than some c?
Okay.
Yeah, I guess I meant infinite is the opposite of finite, so an infinite norm would be not finite. And a finite norm would have some upper bound.
Well, the key is, by definition of what it means to be a norm, which I wrote actually ahead of this slide. So yeah, a norm has to have range not infinity, not including infinity. So you can't have a function, an element of your vector space where you apply the norm on it and you say, oh, that has norm infinity. That's just not allowed by the definition of norms. And that's why the operator norm is not a norm on the linear functions. It's only a norm on the continuous functions, because only on the continuous functions is this finite. If it's discontinuous, then this operator function, you're probably wrong to call it a norm in that scenario, would be infinite. So I hope that answers the question. But yeah, for the rest of the proof that the operator norm is a norm on a space of bounded operators. So as we just discussed, the previous slide shows that on the space of bounded operators, the function, the operator norm, has range not infinity, not inclusive. So this is satisfied. But what's left to satisfy is these 3 bullet points, which are the the things you always have to check by definition of norm. This is the definition of a norm, right? And I think that my colleague went over it in the previous lectures. So what we haven't done to check that it's a norm is check these 3 points. And that I left as an exercise. I think the first and the third of these is not going to be any trouble at all to you. Maybe the second one will require a bit of thought. You kind of have to use the triangle inequality and the properties of the supremum kind of together. But you should definitely have a go at this. And yeah, all the exercises I left in this talk are easily Googleable as well. So if you do get stuck, they're all very standard things to show. And as a little bonus exercise for the proper analysis heads in the audience, we'll talk about completeness, right? So a normed vector space is complete if every Cauchy sequence is convergent to some point. So you don't even need the full generality of vector spaces here, but what a bonus exercise is, and it's a hard one, if you've got V and W normed vector spaces, show that if W is complete with respect to its norm, then B of VW is complete with respect to the operator norm. And this is what makes it a Banach space. So going forward, we're going to talk about adjoint operators. So this is one of the nicest things about Hilbert spaces is the existence of these, and there's a lot you can do with them. Now, there is a notion of adjoint operators in Banach spaces as well, but this is a case where, you know, going into more generality and more abstraction would have made things a bit more complicated. So I kept things on the level of the Hilbert space here. But if you did want to go and study about the Banach space version of adjoint operators, it's not very different at all, just a sort of slight step above, because the domain and codomain of the adjoint operator would, you know, be kind of different in that case. So let H and K be Hilbert spaces, and let T be a bounded operator from H to K. The theorem is that there exists a unique operator T star from K to H, which is bounded as well, for which the inner product of Y Tx is equal to the inner product of T star Y X for every X and Y in H and K respectively. Now notice that the left inner product here is in K and the right inner product here is in H. This is important. Obviously, you can't just take, you know, Tx and X to have an inner product with themselves, because they might be in different spaces. So just make sure you're in the right spaces when you're taking these inner products. T star is known as the adjoint operator of T, also known as the dual operator. So some people call it the dual. We also have the equation, the norm of T star is equal to the norm of T. And this is the operator norm, by the way. Oftentimes in all areas of maths, the little subscripts and stuff sometimes fall by the wayside, especially if, you know, every time we're talking about the norm of an operator, it's always the operator norm. So how do you prove this? Well, first we're going to define a map from H to the field. Remember, this is a real or complex. It's just whatever. We said F could be anything at the start. And it sends X to the inner product of Y and Tx. And we claim that it's a continuous functional. Well, how do we know this? So it's a functional because it's a linear function from the Hilbert space to the field. And we know it's linear because of the linear property of inner products. And it's continuous for this reason. So if I take the norm of the inner product, if I take the norm of phi x, what I'm going to get is the modulus of y and tx inner producted. Now we can use the Cauchy-Schwarz inequality to get this, and the operator norm by definition can be split up in this way. This was one of the little exercises I left for you earlier. So what does that tell us? That tells us that the norm of 5x is less than or equal to the norm of y times the norm of t times the norm of x. So the operator norm of phi, so to speak, is bounded above by the norm of y times the norm of t. And that proves that it's bounded. Now, if you'll remember from the last lecture, the Riesz-Frechet theorem, it says that continuous functionals always have a unique vector whereby to apply the functional is the same as to take the inner product with this vector. That's what the theorem states in loose words. But yeah, the upshot of this is that for phi, there exists a unique vector zy such that for every x in H, phi of x is equal to the inner product of zy and x. And this is just the definition of phi of x here, as we defined in this line. So y uniquely defines this map, phi, and phi uniquely defines zy here. How to define t star? Well, we'll just take the map from k to h, sending y to this uniquely defined vector zy. It's just to check that the domain and the codomain line up. So y here is in k, that's correct, and zy is in h, so that's doing what we want it to, and that's all good. Remember that this inner product on the left here is in k, and this one's in h as well. So yeah, I left the rest of the proof to the reader. We've defined the map, but what we haven't done is shown that it's a continuous operator. We haven't shown that it satisfies this equality, and we also haven't shown that it's unique. So there's some things you can try at home. They're not too hard at all. For people who haven't done uniqueness style proofs before, they're always kind of played by the same tactic. What you want to do is you want to say, assume that T has two adjoints, T star 1 and T star 2. And then from that assumption, you want to, do the steps and prove that T star 1 is equal to T star 2. So that's kind of your tactic for that.
Sorry, Max. We have one more question from Mohammad Riza.
Yeah.
I mean, you can read in the chat. I think it's easy.
Okay. Sorry.
It's about the previous proof.
Amelia, how would B directly imply A? So yeah, we proved that B implies C, which implies A. So in that sense, yeah, B does directly imply A. What does linearity imply in this example for extension from a point to the whole space? I guess, yeah, it kind of goes back to what I was saying earlier. So linearity implies that if you've got continuity at the point 0, then you have continuity on the entire space. So I think that's what you're getting at there. So can everyone see that again?
Yes, yes. I mean, if you want,
Okay.
I can read the.
Yeah, it might be easier.
Yeah. Okay. Next time maybe. Sorry.
So yeah, so here's another bonus exercise. This is something which I thought would be good to include because it brings people back into the wheelhouse of quantum computation and familiar stuff. So everyone remembers this when you learn about inner products. This is one of the first ones they give you. So the inner product of n length complex vector and another one is just this. You multiply the jth components with the conjugate of the jth component, and then you sum them all up. It's the dot product for complex vectors. So also from undergrad linear algebra, you'll remember that on finite dimensional spaces, you can always express these operators as matrices. And then you have action by matrix vector multiplication. So what I want you to do is show that the matrix associated with the adjoint of T is given by the conjugate transpose of the matrix associated with T. And this is something you can kind of do with just a bit of like a very direct approach. And yeah, if it seems kind of too abstract to work with Cn, maybe just try it with like C2 or C3 and then kind of get the gist of it. In quantum physics, a lot of the time, people use this dagger here to denote the star when they're talking about the operator as opposed to the matrix. And either works. It's just something to watch out for. Yeah, here's some other properties of adjoint operators that I'm just going to rattle off. T star star is equal to T. It kind of expands linearly like this, but it's conjugate linear when we talk about the bringing constants in front of them. So it has this kind of property. It's sort of like reverse multiplicative or something. If you take TS and you find the adjoint of that, that's equal to S star T star. And finally, you've got this, which the C star algebraists might call the C star identity. And as an easy exercise, which would definitely be worth trying out, prove the above properties. Yeah, these are all very standard exercises, but once you've got to the bottom of this list and you prove them all, then you'll be very comfortable with how these things work, and just like it just lets you shift operators kind of from one side of an inner product to the other, and it can be very helpful. And lastly, as promised, we're going to get onto the spectrum of an operator. I just wanted to make you guys aware of it more than anything because of how important it is in quantum mechanics going forward. So if H and K are Banach spaces, we use this notation to denote the identity functions. These are just the functions that do nothing. They map an element to itself. So if T is a bounded operator from one space to another, H to K, and there exists some S from K to H such that TS is the identity and ST is the identity of their respective spaces, we say that T is invertible and S is equal to T inverse. It's just like the inverse of any bijective function that you come across in any course. Something also quite easy to show is that if T is invertible, then its inverse has to be unique, and the adjoint is invertible, and you have this, it kind of commutes with the inverse and the adjoint. So these are just some properties of the invertible operators that are worth knowing about. There's a very famous theorem by Banach that states that if we have a bijective linear function, then its inverse must be bounded. So that's a very nice proof. It relies on something called the closed graph theorem, though, so it kind of would have been a bit of a tangent to prove it today, but I definitely would recommend looking that up if you get the time. Okay, so the definition of the spectrum is this. So if we have a bounded operator on a Hilbert space, the spectrum is defined to be the set sigma of T, which is the set of all complex numbers such that lambda I minus T is not invertible. Here's another little exercise to prove that you know adjoints very well. The spectrum of the adjoint is the complex conjugates of all of the elements of the spectrum of T. Okay, so one very nice thing about spectrums is that they always contain the eigenvalues of the operator. Okay, how do we prove this? Well, it's very easy. So if lambda is an eigenvalue of T, then it has some eigenvector x, right? X is non-zero because it's an eigenvector, and lambda I minus Tx is equal to 0 because, well, that's the definition of an eigenvector. Lambda x is equal to Tx. But also, lambda I minus T of 0 is 0. This is just true because this is a linear function, lambda I minus T. So you apply 0 to it, you apply it to 0, and you're always going to get 0. So you have two different elements where if you apply this function to them, you get the same thing, and that contradicts would contradict an assumption that this is injective. So we can't have injectivity in this case, and so we can't have bijectivity, and therefore we can't have invertibility. And in fact, in finite dimensions, we can go the other way. We've got the reverse implication too. The spectrum of T is exactly equal to its set of eigenvalues. In infinite dimension, this doesn't hold though. So if you're looking at more like abstract stuff, you've got to be careful there. And it has lots of interesting properties which are outside of the scope of this talk here. But the properties that I think you should definitely know about is that the spectrum of any bounded operator is compact. And it's a subset of C. So you get this old theorem of the Heine-Borel theorem, which says that therefore it's closed and bounded. It's equivalent to being closed and bounded. So that's very helpful to know. And yeah, that brings us to the end of the talk. So thanks everyone for listening. And I guess I've got time for some questions and yeah.